Okay, well, we have about 20 minutes left of our normal class period. Normally what we do, I think, is maybe start another topic, but since there's so little time left, let's just spend the rest of the time talking about the paper for discussion, and next Monday we'll do some work on hydrodynamic voltammetry, and we'll probably try to get that finished up and start on the next chapter right away, because we're a little behind where I'd want to be at this point. So for the exam now, so we'll include chapter 12 as part of the exam. So what we talked about today will also be on the exam. Mostly, I guess I would suggest most of the stuff that we talked about the previous week would still be on there, but don't expect the stuff we talked about today not on the exam. So we've got where did we start? I guess we started in chapter 5. Is that right? And some of that chapter 5 we had in the last exam, but wherever we stopped on chapter 5 is fair game. So chapter 5, chapter 6, chapter 12. And some appendix B, simulations. All right, well, let's talk about the paper. I thought it was a good one because it talks about self-assembled monolayers and also has some interest for electrokinetics. And so start out by asking for any comments or questions from the students and see what we can talk about.
The alternative is what's meant by perm selectivity?
Perm selectivity has to do with a little bit to the selectivity of a film. So the selectivity arises from the ability of the material to permeate into the film itself. And so some films, because of the partition coefficient, have the ability to allow materials in and permeate through the film. So in this case, the ultra-thin monolayers, because they're quite thin, should not have very good perm selectivity, because there's hardly anything there to keep something out, but they've added a chemical effect on top of it to keep things out as well. So what's the goal of this research? Anybody have any idea what they're looking for? What they want to do, what they want to accomplish, or what do they think they accomplished in this paper?
Sensitivity.
Increased sensitivity for what?
Biosensors?
The sensors?
Biological molecules.
Biological sensors. Why are they worried about it? Why would they have to increase the sensitivity? What's the So they're increase the sensitivity. What's the means to doing this sensitivity increase? What are they doing to increase the sensitivity?
Smaller chain length.
Well, first of all, I guess ultimately they're modifying the electrode to increase the sensitivity, right? They're adding this monolayer of material in there. What else? So what's this monolayer going to do for them? What's the point of the monolayer? It's supposed to increase the sensitivity. How is it going to do that?
Fast electron transfer.
All right. Normally, if I put a spacer group between the electrode and the molecules in solution, I wouldn't expect the electron transfer to increase, would you? No. So why would they think about having fast electron transfer with this polymer film on the surface? Is the goal really to increase the rate of electron transfer?
No, their goal is to prepare some, they say that some new surfaces that have well-known features on the surface that doesn't affect the electron transfer. So they say well-defined electrode surfaces at which surface features such as charge and hydrophobicity can be easily controlled.
Right.
Is that the goal of the production of these new electrodes?
Well, I think that is certainly part of their. That's a very large scale goal, I guess, is to make an electrode with fixed properties. It's always an interest to electrochemists to make electrodes that have different properties and well-defined properties in particular. So at least if they don't know, if it doesn't do exactly what they want, they know exactly what it's going to do. So that's an important aspect. So, but I think there's a reason that they're worried about the kinetics in this for these particular electrodes that we haven't examined yet. What's the? Laura said fast kinetics is important. Imad says fixed or well-defined electrodes are important. Which is so how do these come together to produce a more sensitive electrode?
Control the electrochemical response.
Right. How are we going to control it? What's the control mechanism here?
Well, they can make the surface more or less hydrophobic.
Right. So how's that going to help us? What's the hydrophobicity have to do in there?
We're going to increase the kinetics
Of what?
of the biological molecule
Why? Why would it make any difference?
because they're slow on a bare electrode.
Yeah, but you're kind of arguing in circles here. Let's
Yeah, but
What is electrode passivation?
electrode passivation means that you somehow made the electrode inactive. You deactivated it. So
This is done by a co-assembly of one more hydrophilic part and more hydrophobic part.
yeah.
This is just using thiotic acid. With
Yeah.
one. This is the one.
Well, okay, right. They're putting whatever whatever it is,
Thiotic acid
thioctic acid. Yeah.
and one hexane thiol. This is more hydrophobic.
Right. So with the thioctic, what's it have on it that's going to make it something to be interested in?
Carboxylic group.
Right. So it's got a carboxylic group at the end. And what chemical properties is that carboxylic acid giving us to the film? What's it? Hydrophobic.
Hydrophilic.
Hydrophilic.
Yeah, hydrophilic.
Water, it's going to be under normal conditions, under reasonable acidic conditions, it's going to be deprotonated, or under normal neutral pH, it's going to be deprotonated, right? It's going to have a negative charge on the thing, and they're doing experiments under essentially neutral conditions, I think. So with the thioctic acid is going to add some aspect of negative charge at the end of the film, and it's also that's also a hydrophilic layer on the end, right?
It increases, they got fast kinetics on the surface.
Right. And so why are they mixing those two together? Why are they mixing the neutral and the thioctic acid monolayers together? What's the point of that? Why don't they just, that seems to be an important thing they're talking about.
To give order to the monolayer?
Yeah, it keeps it ordered, I suppose. You want a well-defined surface, but you also want to titrate in the amount of hydrophobicity, right? You want to be able to, just by changing the relative differences in the relative ratio of those two, you can make it all neutral or all active or all basically hydrophobic. So you change the ratio of hydrophilic, hydrophobic, hydrophobicity on the electrode surface. And that's kind of their game plan, right? They're going to try to turn a knob, change the ratio of those two, and so try to run the gamut from a very hydrophobic to a very hydrophilic surface. And what's the reason why biological materials in general are often problematic at normal metal electrodes? They mentioned that. Do you remember seeing that? Why is it a problem?
The reactions are reversible.
Yeah.
Bare electrodes with biological substance.
All right, it's the same problem we talked about just today in class with NAD, NADH, electrochemistry. It's irreversible. It tends to, once it oxidizes, it tends to stick and decompose on the electrode surface. Usually because the metal has enough catalytic activity just as a metal to cause these things. Also, these materials are very large generally, so in general they prefer to be absorbed to some surface rather than being present in solution. So if you mix, so what would happen? Suppose you had a material that was very large and bulky and had a positive charge on the electrode. A protein, for example, may or may not have a positive charge, but it probably does. A lot of times it does have a positive charge. What would happen if it comes to this thioctic monolayer, and what's going to happen to it? Is it going to be attracted, repelled? Is it going to be faster, slower? Probably it's going to be attracted, right? Because there's electrostatic interaction there. But suppose it's attracted so strongly that it sticks to the electrode surface, or sticks to that layer, never comes off. Is that what we want? No. Yeah. So one of the things that they were interested in doing is for a particular type of analysis, they can dial in just enough hydrophilicity or neutral or negative charge to attract a protein to the surface and to allow the reaction to take place, but not so negatively charged that it sticks. So they can adjust that ratio of different things. They actually didn't use proteins. They used some charged species, ruthenium hexamine and ferrous cyanide. They talk about the capacitance of the electrode. I'm not sure that's that critical. You can see they've talked about the phi-2 effect and so on. One thing that you should note is that the dielectric constant, the capacitance of the electrode, let's see, it changes quite a bit depending on the material. Now they say that the bare electrode has a capacitance of 72 microfarads per square centimeter. That's on page 2770. With the monolayer on top, you see much lower capacitance for the C6 style, 2.7 times 10 to the minus 2 microfarads per square centimeter. So there, that monolayer is acting basically as a spacer group to get the ions away from the electrode surface, decreasing capacitance. Also the dielectric constant, also tabulated there in table 1, is low, so the capacitance also drops because the dielectric constant of that film is low. So essentially you're adding a layer of plastic on the metal surface, a very thin one, but that's what you've got on the electrode surface. It's not like plastic well, it's like plastic, but it also is it's thin enough that the material could actually get through the surface as well. So let's look at figures 1 through 3. Can we explain the results of the figures based on the monolayer type? Let's look at figure 1. The solid, let's go down and see, the solid line is TA monolayer. TA stands for what? Thionic acid. Okay, so what's that kind of surface? That's a hydrophilic surface, correct?
Mm-hmm.
So we expect that that surface would be, well, it's negatively charged, so the ruthenium hexamine is going to be attracted to that surface most likely. So you see really very little change. They don't really show you what happens if it's a bare electrode, but a bare electrode you'd have a very reversible looking wave. With the 1-to-1 ratio of the alkane C6 monolayer, you see basically no difference. If it's 1 to 100, now what happens to the response? It drops.
Becomes really similar to the background.
Right. Why does that happen? What do you think?
No interaction, so it's not able to get in there, or it's not packed right.
Right. Well, yeah, the rate of electron transfer obviously has dropped significantly. It's not zero because there is, with the 1 to 100, there's still some current increase there, suggesting that there is some electron transfer occurring. But it's very low. So what explanation could you come up with for why the rate would be lower? I mean, you're attracting it to it, but that doesn't necessarily mean it's being repelled just because it's a neutral end point, right? Is there any reason to think that there's a repelling of the ruthenium hexamine molecule? You've got, at the end, you've got this alkane. Here's your ruthenium hexamine. Is it going to be repelled by that alkane end? No. I mean, if that's carboxylate at the end, it's going to be certainly attracted to it, right? But it's not going to be repelled. The neutral. So why is there a big difference in the rate? What's their explanation for that?
You really didn't give an explanation, did you? For that one? It just says the response becomes indistinguishable from background current.
No.
Well, it said, similar results have been previously reported, but no satisfying explanation has been given in the literature.
Yeah.
And then they said the simplest explanation is that the high charge density of the ruthenium hexamine higher than the ferrocyanide prevent its access to the hydrophobic surface.
No. Yeah, it's hard to know. I think a reasonable explanation is that the reason they're getting electron transfer in the normal film is that it's not very ordered. In other words, we expect the film to all line up like so, marching along. But in fact, it's probably likely that with the mixture especially, you don't see a selective film in the sense that it's completely ordered and preventing material from getting in. Or you can get the electrode, the material can be inserted in the film enough to get some electron transfer to it. Whereas with the more high proportionate of the alkane thiols, they're very ordered. And so there's no way for the ruthenium hexamine to get close to the electrode surface, and that's probably the reason. And you can compare, excuse me, I'm sorry. You can compare that to, and the reason that you see it with, say, if you look at figure 2, pH 1.5, you see a a nice curve. And so what's happening at pH 1.5 that's different at pH 7.4 in figure 1?
We have carboxylate group is not ionized.
Hydrophilic?
It's
Yeah.
not ionized.
Yeah, the carboxylate's not ionized, right? It's pKa is carboxylate's about 4, so 4.7. So we expect a neutral surface there. So should we, again, we don't really expect any disordering or any, I guess I should say, any repelling of the surface. In other words, we've got a negative ferrocyanide now in a neutral species. Again, just like ruthenium hexamine, we don't see any repelling of the surface, but unlike the ruthenium hexamine, on the neutral species, on the neutral surface, now we see good results, and so that's the reason for the disjoint in their explanation. They don't understand why the neutral surface in figure 1 and the neutral surface in figure 2 give such different results. I think it's probably because in figure 1, even this neutral surface is still not as ordered as the neutral surface in figure 2. The neutral surface is not as ordered as the neutral surface in figure 1, and that's probably the reason. And the addition of the alkane thiols adds additional amounts of ordering until you get a reasonable blocking of the behavior. In figure 3, now you see what you'd expect with the pH 7.4. Now again, ionized carboxylate groups will completely block the ferrocyanide. That's the solid line there, right? Because even if it's not ordered, we still have a large amount of negative charge on the surface of the electrode, right? It's negatively charged, and so we don't have to have an ordered surface to block things. It's got this large charge on the surface. And then as we put in more of the monolayer, alkane monolayer, it becomes more ordered. So the data, you kind of expect that figures 2 and 3 for the C6, the C6 style monolayer, which is this kind of drawn out wave there, and this C6 monolayer here should be similar, and they're not that similar. So there's a question there is still that pH difference there. So they have a fairly complicated set of data there, but
The solvents are, the electrolyte is also different in figure 2 and in figure 3.
yeah.
There they say that perchlorate form a salt in the surface and limit also the reaction.
Yeah, that's possible. It's a possible thing. All right, they did do some biological-like molecules with quinone and dopamine, but so what's the basis of their, again, the conclusion that they may have a more sensitive or selective monolayers? What's the selectivity going to be based on? How are they going to selectively detect things with these sort of things? And we talked about it, but let's summarize.
The head group
Right.
could be changed in different pHs.
Right, we can basically, in this idea, we can dial in the hydrophobicity of the surface, changing it to whatever we need to be, to say, make sure that only cations or only anions get near the surface to be detected, right? So why would that increase sensitivity? What will we have done if we do that to make the sensitivity of our electrode better? Would it necessarily make it the response of for a particular molecule larger? Did we see any evidence of that? I mean, you can think of sensitivity as, okay, I've got more signal for a given amount of material, right? So do we see evidence that we got more signal for a particular molecule? What about we didn't look at dopamine. What about dopamine and Dopac? It's possible we could.
Yeah, or hydrophilic.
Yeah. It's possible we can if we have a material that absorbs onto the surface, and because the response is proportional to the scan rate, we might increase our current because we've got a higher signal because of the absorption rather than a diffusion-based process. But sensitivity just doesn't rely on the fact that you may have a higher signal. It also relies on the fact that your noise level has decreased as well. So sensitivity is not higher signals. It's a higher signal to noise ratio. So if we have a high background signal and a high signal from the material to try to detect, it doesn't do us much good. So even if we keep the signal the same, if we can lower the background on our material, then that's as good as increasing the signal that way. So sensitivity can be improved not only by increasing the signal like we see maybe with dopamine, but also by lowering the background due to, say, things like anionic impurities or something that we'd like to exclude from the electron transfer process. That way. A big one for biological materials is ascorbic acid, ascorbate, which is present usually in excess or larger concentrations, say dopamine, and it's a neutral, it's a negative species. So in this case, dopamine, positively charged species, and the neutral will exclude, then the film will exclude ascorbic acid because it's a negatively charged species. Well, we better stop here, and we'll see you on Saturday, I guess.